Welcome to the final lecture of Intelligent Product Design. Today we will take up a case study and I will give some closer statements for the intelligent product design. Okay? And for this purpose we have taken one of the best system that has been developed at the SMSS laboratory of IIT Kanpur, and this is a robot for power substation inspection. It is called Substation Inspection Robot or SIR, okay? And this has been developed by a sponsored project from Power Grid. So, let us just talk about this intelligent robotic system. Now, as you can see that there are many critical areas in a power substation. Okay. On our left you can see that there are areas where you can have navigation challenges, okay, like pipelines, like chambers, okay, also climbing of stairs. Then there are certain obstacles that you need to overcome, this type of obstacles, okay, in a substation. Then the paths, sometimes the paths will be very good, sometimes the paths will be full of stones because there are some insulation requirements there. Now, the most important thing that we have to do is that we have to understand the certain quality of the level of insulations etc. through the instrumentation. That means, we have to read the readings of the instrument and then translate it in terms of numbers or digits, so that the people who will be doing the analysis at the control panel inside a room will be able to know about whether there is any change in the system or not. And this is very challenging. First of all, manual checking of all this type of system is discouraged because of very high electromagnetic flux density. And secondly, I told you that if you have a robot, you get actually all weather report of a system. So, which that frequency you can get is enormously high, the data density will be enormously high. So, that is why such a robot is extremely required. And you can see the number or type of panels. There are many different type of panels. There will be challenges of reflections, dust accumulation on the system. So, all these things had to be processed through the image processing part. I have already talked about the obstacles that it has to actually overcome. Now, what are the possibilities for us? First of all, in terms of a vehicle, we can design a four-wheel system, or we can design a kind of a rocker bogie system, or we can design a quadruped system. All the three type of systems are available today. Now, what are the advantages or disadvantages? If I use a four-wheel system, then it is going to need at least 4 servo motors, and also there is a pan tilt option. So, another 2 motors there will make it actually 6 motor system. On the other hand, if you go for a rocker bogie system, you would need 6 motors for driving plus 2 pan tilt will make it 8 motor system. And on the other hand, for a quadruped you need 16 for driving and 2 PT, that means 18 motor system. Now, you may tell me that why I am so much bothered about the motors. Well, that is because in such robotic systems, motors are one of the most expensive part. The lesser the number of motors, the better will be affordability of the system, and the design complexity also will come down. So, now what stops us then for using the least number of motors? Well, one obstacle is that the payload capacity. This 4 motor system payload capacity is about 50 kg. On the other hand, so you can keep the payload to be high, but what you are going to suffer is that it will be not be able to do some high performance works, like some kind of dynamic stability. For example, if it has to climb stairs, or if it has to cross some obstacles. On the other hand, if I go for 6, I will slightly sacrifice this 50 kg to 20 kg, but what I am going to gain is in terms of the dynamic stability of the system. and that also increases sometimes the maneuverability of the system, because you are going to have a separate system for the steering and a separate system for hauling the loads. Now, you can get the highest degree of maneuverability and obstacle avoidance if you go for the quadruped robot. But then what is it that you will be sacrificing there? The load capacity, because the load capacity is only 10 kg. In terms of the control scheme also, the four-wheel system is very easy, whereas this is the most complex. So, somewhere in middle comes this modified rocker bogie system. Maneuverability I already told you. As a result of all these critical comparisons, we thought our design must be based on a modified rocker bogie system. Now, having identified the first part of it, then we have to develop the CAD design, and we have to also simulate the motion. The motion simulation, I have already told you that there are various artificial motion simulation platforms like Gazebo, where you can construct artificially all sorts of obstacles and check how the robot is going to move. So, we have done the same, we have developed the CAD model of the system, and then we started running them, for example, in different kind of undulations and also in stairs, because that was another challenge, that it has to climb the stairs, and based on which we have developed and redesigned the CAD model, the initial CAD model. And then inside the CAD model also we have to have scope of developing the circuits, the microprocessors and the microcontrollers. So, all the drives, processors like NVIDIA O-ring and other processors, then the cooling block, and then the battery pack, most importantly the power part of it, and all these other paraphernalias for the system are to be accommodated, and then the total load is to be rechecked, because we already know that what is the kind of carrying capacity against each size configuration, which is constrained by the number of motors that you are utilizing. So, you can see a typical motion simulation on a stair, how it is going to happen. You can also see that for uneven terrain how it is going to move. Now, this kind of simulation on various terrains can be further done in a much more sophisticated environment called ADAMS. So, you can see here the ADAMS movement in a ADAMS simulation platform, and how this robot is moving and what is the kind of vibration or displacements that is coming up into the system. We have also done it for different types of situations like on sand and also on mud and soils. So, for different type of field conditions, and finally, we have also done it for the uneven terrains. So, once in all the cases we actually run our robot and see that a satisfactory movement is possible, then only we start to develop the prototypes of the system. So, now while developing the prototype, the first important part is to acquire the sensors. So, let us see what are the sensors that you must have for such a system. Well, one important group of sensor is related to the thermal camera, which must be of very high resolution, because this thermal camera is supposed to sense if there is any hot spot. Okay. So, then it should be able to say that there is a high temperature developing, there is a possibility of short circuiting. Then also you need to have CMOS camera with optical zoom, so that you can read all the different dial gauges, and this should be sort of placed on a pan tilt kind of a platform. And then you need another camera which is called a stereo depth camera. This is needed mostly to see what is there on the path of the robot and to help to create the map of the path of the robot or the trajectory of the robot. Similarly, with stereo depth camera, you will need a lidar, so that you will be able to know the obstacles and the trajectory of the path. And then you would need processors like Raspberry Pi and also O-Ring, which is a high performance onboard processor. That is one of the most expensive processing system. And finally, last but not the least, you need the motors, as I told you, and here the Maxon DC motors has been used extensively in this particular system because they can give very large torque. So, some of the sensor specifications you can see here: thermal camera specification, then CMOS, LIDAR, stereo depth camera, microphone. Microphone is required in order to hear the sounds, particularly in such kind of a substation. The sound from systems like a transformer is absolutely important, because then you will be able to know whether the transformer is healthy or not. If the noise pattern changes, then there is always a possibility of the transformer is going wrong somewhere. So, then the microphone is required for this purpose, and onboard processors I have already told you. So, these are the elements that are going to give intelligence to the passive robot. You can see that how the entire thing needs to be hardware developed, and the entire thing has been developed in the SMSS laboratory by an extensive range of work. Now then, once the prototype is developed, we first need to check how it works, right. So, you can see how the chassis is working. So, how it is able to actually cross some of the obstacles in the form of bricks, etc. Then on a gravel, how it performs, that is absolutely important. So, we can check that how it is moving on the gravel. You can see at this moment it is a functional prototype, because you do not have the complete coverage, you need only basic functional requirements, and in fact the power also sometimes you do not need a battery, but you can supply a power from outside just to see how the system is working. So, this is robot running in a gravel terrain. And finally, I told you that this robot has been designed such that it can even climb the stairs. So, you will be able to now see that how the robot can climb the stairs. So, you would be able to see both the downward motion and you will be able to see the upward motion in both the cases. Now, as I told you that in both the cases, when testing this system, we did not put these O-ring based microprocessor, but a simple laptop would do, they can do the processing work. So, you can see both the type of climbings and all obstacles that it can actually take care of. Now that your robot is that is substantially strong to handle all sorts of obstacles, now it needs to do the work. Okay, what are the works? First work is autonomous identification of the reading of the analog gauges, like here. So, first of all it has to know where the analog gauge is, and then once it identifies, it has to put a bounding box, then it has to start to read the reading of it. Second work that it has to do is to identify the hot spots on all critical components, such as you can see that some hotspot identification is again happening in the system. Third is capturing of the acoustic response from transformers and reactors. The sound recording is something that it has to do simultaneously. Then it has to look for cracks and chipping of insulators. So, it has to study each of the insulators and see whether there is a telltale sign of crack or chipping. And then of course, intrusion detection, because if there is a human presence who is not authorized, it has to detect immediately, or if there is some animal, because it is highly dangerous to allow anybody unauthorized inside such a high voltage substation system. And then finally, it has to generate reports of its inspection, whatever it has observed, and it must be having a wireless charging system in order to charge itself whenever it is going to go low in terms of the battery charge, and it must have a 3D mapping of the substation available with it, so that it knows that where it is placed, so that it knows about its possible trajectory. Now, I will show you that in a actual substation how this robot is running, and you see all these areas, these insulators that are there, and then there are these hot spots that are there, all these, and then there are these dial gauges. All these are the areas which it has to continuously locate, identify, record, and also if there is a warning it has to understand and talk about it. So, this real time gauge detection and reading is done through this DNN model, and it can read 17 different type of analog gauges for which it has been trained, okay, through this supervised learning system. And similarly, the region of interests also, that what are the region of interests where it has to look for. Now then you can see a typical manifestation of the gauge reading capability. So, as it is moving, you can see now it is very close to these gauges, and you can see in the inset that it has been able to detect the gauges, and then not only it will detect the gauge, but also it will start to put the readings corresponding to each one of them. Here there is a very interesting sensor that it has, something called a SF6 sensor, which actually detects the presence of if there is any gas leakage that is happening in the system, and then it creates a report where it says the results normal, 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 or something that is of warning. Now, for such a critical system, ultimately it has to be used by some technicians. So, it is absolutely imperative to design an user interface so that they can look for the data accurately wherever they are looking for, and also you can get all the data in a formatted manner. So, as you can see that on our left we have this entire instrument panel that is there, okay, and all the corresponding data are coming up there, and on our right you can see that there are all these different asset lists. So, it is going to talk about that whether the robot is going through each one of them or not, and as it is traveling it is going to detect the asset ID, asset description, location, etc., the corresponding thermal camera reading, robot's temperature, ambient temperature, and battery. This you have to always keep track of so that the robot itself is healthy, and then the capturing mode of all the data, and then the stereo camera streaming of the data, and the acoustic reading, as I told you, corresponding to the transformer and the reactor. Now, you can see the full system how it would look like. So, you can see that the PTZ CMOS camera is here, okay, and it is pan, tilt and zoom, so that you can change the height of it. You can also change the zooming distance inside, and you can also tilt it, okay, to different directions, so that you can go to this way, you can go that way, wherever you need. Then you have the IR camera that is placed here, okay, and that can sense again in terms of the temperature. Then you have the leader here in terms of the obstacle. Stereo camera is placed close to the road because it has to look into the road quality, the road trajectory and all the things. Microphone is co-located with the IR thermal camera. These placements are very important because two things. One is that it has to be very compact, and from the electronic systems point of view, similar type of power requirements should be gathered together, and also you have to think of it with respect to the CG, how you should place it so that the system remains very stable. And so, for this IR camera and this system, the microphone, there is also a modular pan tilt unit that is there, and that this is the level of the specification. So, you can see that the entire system is about 70 kg of weight, and the rated payload that it can take is 30 kg. Velocity is about 0.5 meter per second, just like walking speed. The battery capacity is such that it can go up to 2.5 hours, and the wireless charging time is 1 hour 10 minutes. Endurance of full load is 3 hours. So, that means after every 1 hour approximately of charging, in 2.5 hours it can go all around the substation, record the data and come back. It has also some additional bumper sensors here, so that if there is any really hard obstacle, it will immediately stop, it will not move. and you can see the chassis, of course, that we have seen it earlier, which is a modification of a rocker bogie mechanism system. So, this is the entire system in its close view. I will now show you that how it is moving in the night, because I told you that it has IR vision. So, how it is moving in a very low light condition in the evening and in the light night situation. Even in that time it is capturing the images here, you can see it here, okay, which is actually it is so far away. So, that it uses a 32x zoom CMOS camera in order to do this work. And you can see how this zooming is happening, and it is able to get the reading after successive zooming of the system. So, now that we have done all the case studies, so I am now coming back to where we started the course. Okay. I first want to tell you that design of intelligent product is something which is there in our blood. Okay. It is something that is not new for us. If you look at Professor J.C. Bose, his contribution, it was tremendous when he said that how he has been able to find out intelligence in inert materials and plants with the help of developing systems like this, which is a crescograph, and it is so good that it can actually magnify the very little movement of a plant by 10,000, 100,000 times. So, it is such a sensitive machine and it is still working today. So, for intelligent system design, the high machining capability that is needed in our country, we have already demonstrated 100 years, 150 years before that kind of capability is possible. So, we should not shy from it, right. The other important point is that as we are gradually making higher and higher precision sensors and actuators, we are gradually merging the barrier between something that is living in a natural sense and something that is developed by us. Like in nature, you have the intelligent systems all around, including us. With the integration of all these sensors and actuators, we should be also able to design systems which will be of having at least some level of intelligence comparable to these systems. Okay. So, the difference between non-living and living is going to get completely breached, okay, and the endeavor that Sir J.C. Bose had taken long before, that dream would be fully realized. So, this is one point I want you to take home. Second point I want to tell you is that whenever we develop something intelligent, there is an international standard of Turing test. This test was originally proposed by Alan Turing in 1949, and the test was related to a machine's ability to exhibit intelligent behavior which is equivalent to that of a human. Now, the original test was for an imitation game, because what Turing thought is that the indistinguishability is possible in two ways. One is through verbal communication and another is through the non-verbal functional means. But the functional capability of a machine in those days was not so high that it could be actually challenging a human being. So, you can easily distinguish you could have in those days. On the other hand, he focused more on a verbal system, so that if you sort of keep the machine in disguise, nobody watches where the machine is, nobody watches where the human being is, and then ask the same question to the two who are hidden and then see their response. From the response, can you make out which one is coming from the machine and which one is coming from a human being? And then if you can do the differentiation between the two, then you would be able to say that yes, the machine is still not that intelligent, but if it becomes indistinguishable, it is going to pass the Turing test. Now today we are actually coming to a case where the non-verbal Turing test is possible. This idea was there in the Gulliver's Travel, the Jonathan Swift, when he had been to a kingdom of this Brobdingnag, there the king thought that Gulliver must be a piece of clockwork contrived by some ingenious artist. Okay. So the idea was there, but the problem is that people didn't know. They thought that only through a high precision clockwork we would be able to achieve it. But we now know today that without the help of all these sensors, actuators, without the help of a complete electromechanical system, we won't be able to achieve it. So, when actually Turing proposed that can machines think, what we want to say now is that can machines do what we can do? That will be the new paradigm of artificial intelligence and intelligent system design. And if we can do it, then we will be able to ask the next question, that are physical and thinking ability both of a human and machine, they are indistinguishable or not. One important obstacle towards this is to make an IAS system energy efficient. In order to do it, we have to offload some of the computation from the O-ring system to the morphological system on the body of the system itself. This is what is called morphological computation. I have not touched these issues in this course. I intend to actually teach this part in an advanced course on the basis of this further. Then we have to also talk about the passive dynamics, because the dynamics of the system should be inherently stable, and we should be able to, if we can take the advantage of the passive dynamics like a passive walking robot, we can actually minimize the number of actuators to a large extent. Material intelligence, as I told you, that the application of smart material can cut down on the cost of sensors very heavily. So, material intelligence is highly important, not only for sensors but also for actuators. For example, if we can replace motors by shape memory alloys, that will be much more desirable in terms of making it more energy efficient. Compliance and adaptability. As I told you earlier also, that a telltale sign of an intelligent system is it is adaptive to the change of environment. Now, if you can make a system compliant, now if it is too much compliant, it won't be able to carry a load, but if it is reasonably compliant, it will be adaptive as well as it will be able to do all the functionalities that it is supposed to do. So, this is important. We have to know how to incorporate compliance in the system as and when required. And most importantly, never forget about the bio-inspired design. Take always cues from nature. This is the way to make it more energy efficient. But the key thing is that we need more of physical intelligence, because if you only rely on soft intelligence which is based on computational capability, then it will never be energy efficient. So, you need to have more physical intelligence. How we can have it? One way, as I told you, if you have a hierarchic configuration of shape memory alloy wires, which actually pulls some system like this, and that pulls a main system. So, that way you can make a very compact, intelligent material driven hierarchical actuator system. If you look at our body, our muscle structure is exactly like that. It is completely hierarchic in nature. Now, you not only would need artificial muscles, but you will also need controllable compliant structures. That means you need metamaterials, programmable materials, and microstructured auxetic materials in order to design such a system. Metamaterials are an exceptional class of synthetic materials which is geometrically patterned in such a way that you can create negative stiffness, negative Poisson's ratio, and negative mass. You can actually make it programmable, so that you can do it in each one of these lattices, and that will change the entire property of a system. We have already talked about the possibility of such a system. You can see it in one of our papers where we have discussed this, that how you can jump in the modulus of elasticity with the help of this kind of a system, from a lattice to the macro scale material. I want to tell you also that sometimes patterns can give you a lot of power. So, this is one of the pattern searching we have done in Itmat-ud-Dawla in Agra. It is a wonderful place to visit, and there we have discovered hundreds of such patterns. Okay? We have talked about it in one of our papers which is archived recently, and then all these patterns we would be able to recreate it. What these patterns are going to give us? These patterns are going to give us new metamaterials which can give us more control in terms of the compliance, in terms of the other mechanical properties of the structure. Now, what will happen to our robots when we can give such physical intelligence? I will just show you in one slide what can happen. As you can see here, that this is one of the robotic grippers that we have developed, which can handle a very soft object like a tomato. So, a kind of a very soft and irregular geometry can be actually handled because of the presence of such compliant systems inside it, and that are derived from those metastructures. I will also show you another thing that will drive us tomorrow. This is because this joint is a metastructure joint, so that a new bionic arm can be developed with the help of such metastructure joints. So, that is another advantage of such a system. Now, let us look back. We talked about the original proposition of Turing. Can intelligent machines be indistinguishable from the humans? We have interpreted it in terms of functional, behavioral and aesthetic properties. We have explained our endeavors on the first two parts, functional and behavior. There are some important elements that I have not discussed, that is, according to Turing, storing, execution and control, all three are important, but I have so far talked about executive units and control, actuators and the processors. Storage is also equally important. Can we use such materials for peripheral memory? That is something that I would be covering in my next course. Till then, let me simply quote: animals produce and maintain themselves, grow and develop, while robots are extrinsically built. We built them. They are not born and developed, but both are made of interactive materials and may share organizing principles that allow them to accomplish things in the real world. That makes all the difference from the today's AI system to the system that we are planning to develop, because they are going to interact in the real world, not in the virtual world. We can design a robot solution, pretend we forget it, and then compare our answers when studying such robots and animal behavior in a homologous situation. Building machines having animals in mind has further benefits. We can test ideas in the real world rather than in the idealized realms of numerical simulations or the disembodied conceptions of numerical or neural processing. Robot behavior faces the same physical constraints as actual animals, and our whiteboard models and computers cannot do it. This is something that I am quoting from the editorial on emergent behavior in animal inspired robotics. This is something which must benchmark us in terms of intelligent product design. I hope you have enjoyed the course. If you have any inquiry, if you want to work in our wonderful laboratory with the wonderful people, you are always most welcome. You can contact me. Thank you.